All right, over the past few weeks, we have basically seen the important role a cavity and a population inverted medium play in the making of a laser. A cavity essentially means two high reflectivity mirrors placed parallel to each other at a given separation. And a population inverted medium, on the other hand, involves a system in which level with higher energy, say 2, has more population than a level with lower energy, E1. From Boltzmann thermal distribution of population, we know that in reality, the reverse is actually true. That is, the energy with higher population has always higher, at a level with higher energy, always has less population than a level with lower energy. But if we can create a condition where more population reside in a higher energy level as compared to the lower energy level, then we call that we've created a population inverted medium. Such a medium is called an active medium. That is a medium in which gain has been created. We of course have also studied how to create population inversion, and there are various ways to create population inversion. Now, if we place such an active medium inside a cavity, active medium inside a cavity, then we know that stimulated emission, which is actually seeded by emissions of photons arising out of spontaneous emission. Some of the photons, spontaneously emitted photons, which travels along the axis of the cavity, they can seed the stimulated emission. And the stimulated emission, by taking advantage of such a population inverted medium, can actually allow amplification of light. The light basically oscillates to and fro, back and forth inside the cavity. And every time the light travels through this active medium, it is amplified. So the intensity of light builds up inside the cavity. And if both the mirrors have very high reflectivity, say 100%, then the intensity of light inside the cavity will continue to grow, as there is no way that the light can leak out of the cavity because both the mirrors are having 100% reflectivity. However, if we provide an appropriate transmission loss to one of the cavity mirrors, so this mirror, then a part of this light that is going inside the cavity will couple down as an useful loss, which will form the laser output. And we of course also know that you cannot increase the transmission of the cavity to any higher value, because we also have seen that for lasing oscillation to be sustained, the gain of this active media must be more than the loss. Loss in this case, of course, the transmission loss that we provide to one of the mirror to couple out the part of the mirror. Therefore, the loss of this transmitted mirror has to be below certain value. Otherwise, the oscillation would not be sustained and lasing would not occur. We also have seen that if we involve only two energy levels, then oscillation, amplification of light is not possible. That means we have seen that in a two-level system, amplification of light is not possible. For amplification of light, we have to involve at least a system with three energy. Only then amplification possible. However, adding one more energy level, making it a four level energy scheme, it makes the laser most ideal. We also have refreshed our mind on some important properties of light, such as reflection, refraction, dispersion, interference, diffraction, scattering, and polarization of light, which have important bearing on the operation of a laser. We have tried to understand this in briefly, not in much detail though, to the extent that would be essential to understand the operation of different kind of lasers. So with this, we have more or less completed the first part of our first part of this course, namely an elementary introduction to lists. So now we are in a position to move into the second part of the course, which basically is understanding the operation of a few specific laser systems, important laser systems, which have diverse application in our day-to-day life and also in the advancement of science. However, before moving into specific laser systems, it is essential to gain an insight on continuous and pulsed operation of the lasers. You see, the familiarity of humanity with continuous and pulsed sources of light, both natural as well as artificial, dates back to almost out of mind. The most glaring example of a natural continuous source of light is, of course, our sun, which, as we know, has been illuminating the entire solar system incessantly from time immemorial. From the humble beginning of campfire, the man-made continuous source of light today have progressed to very sophisticated variety of continuous source of light, which has many important applications, which was unthinkable some time ago. The familiarity, or that a light can also be emitted in a pulse mode, was perhaps perceived for the first time by our great predecessors when bright filamentation pierced the sky at the time of a thunder shower, and the development of pulse sources of light that began its humble beginning from perhaps the flash of light that our great ancestors created by rubbing one piece of stone with another, today have progressed to the point, and it has actually resulted in evolution of civilization, today's civilization. Now, as a conventional source of light can be operated can exist both in the continuous and pulsed form, it's no wonder that laser 2 can also be operated both in pulsed and continuous mode, just like a conventional source of light that can be both natural as well as man-made. However, and no wonder that the very first laser that Neyman operated in the summer of 1960 operated in the pulse mode, which is actually a ruby laser, and it was pumped, as you know, by a flash lamp which produces pulses of light, and the laser, every time it was pulsed, it was pumped by the flash source of light, is the ruby rod, it emitted pulse of light. And every time it was pulsed with this flash of light, it would produce pulse of. So this was the first laser, which was a ruby laser. And not long after, in the winter of the same year, 1960, I think December 1960 to be exact, Ali Jahan and Iranian American scientist and his co-worker developed the next laser, which was a helium neon laser that operated continuous mode. That means it emitted light continuously in time. So if we plot the power versus time, it emitted, this is 0, it emitted light continuously in time. So this was a continuous working laser, which is also known as continuous wave laser. Now, before we move into any specific laser, let us try to go a little deeper on the general working principle of continuous and pulse laser. See, if you have to make the laser work in a continuous mode, then understandably, the population inversion also has to be maintained in a continuous fashion. Because only if there is population inversion, there will be gain. So amplification of light is possible by stimulated emission of radiation. So maintaining population inversion continuously means the pumping also has to occur in a continuous manner. Now let us first consider the example of a laser based on a three-level energy scheme. And let us see whether such a laser can be operated in a continuous mode. If there are any challenges to operate such a laser in a continuous mode. Now, as you know, that in such a laser, that is a laser whose operation is based on a three-level energy scheme, initially the entire population reside in the ground or the level with the lowest energy. So initially, all the population resides in this level, which we call E0. And as we begin pumping, the population is first transferred to the pump level, which we call E2. And then it relaxes immediately, usually through non-radiative process, to the upper level. So as we begin pumping, the population from here actually starts getting transferred to the upper. And lacing would begin only when there exists a population inversion. That is, this level, which we called E2, that is the upper laser level, the population here exceeds that in the lower laser level, which is also the source level. That means the entire population initially reside in this level. Now you can realize, because the entire population reside in this level, in order to maintain population inversion, we'll have to transfer at least half of this population up here, of course, via the pump level. This is the pump level. This is upper laser level. This is lower laser level, which is also the source level. Now, it would be a Herculean task to transfer this population to the upper laser level. Actually, to appreciate this point, let us consider a very simple case. That is our lower level, which is also the source level. In the beginning, suppose us 9 atoms. Although we are saying atom, but the inference that we draw would hold true for any other species like molecule, ion, or whatever that makes the species of the active medium. Now, as we begin pumping, we start transferring population from this level to the upper laser. So 3, 4, 5. See, the moment we have transferred 5 atoms from the lower level to the upper level, the upper level now has 5 atoms and the lower level has 4 atoms. So that means we have created population inversion. But don't be too excited. What happens as the onset of lacing begins? Because now you have population inversion, so the condition is right for amplification of light. Now, for amplification of light, there has to be emission of photons. Now, as a single atom comes down to the ground state, makes a transition, and of course it emits a photon of frequency, which would be E2 minus E0 by H. That will be. The population inversion is killed because now the lower level has 5 atoms and the upper level has 4 atoms. So, with only one excited atom making a transition to the lower level, the population inversion is killed. So, in order to maintain this population inversion, always more than half of this initial population, which is 9, have to be continuously transferred to this level, else lacing will cease. Now, to make it a simple case, we have considered 9 atoms, but in reality, there will be innumerable number of atoms, and just think, to transfer each atom from the ground to the lower laser level to the upper laser level, an amount of energy, this much, is expended. This much energy is expended. E1 minus E0. And for every atom that would be transferred to the upper laser level, this much energy needs to be expended. So as I said, it would be a Herculean task to maintain population inversion in such a 3-level laser based on such 3-level energy scheme, because huge number of energy atoms to be continuously transferred to maintain population in a continuous manner. And thus you see, operating such a 3-level laser based on such three-level scale is impractical. So, what would be the remedy? How can we operate a laser in continuous mode? Well, of course, the best way, best remedy would be to add another energy level to this, that is, make it a four-level laser based on four-level energy scheme. Because you see now you have four. So now this is the source level, which initially in which initially all the population reside in this level. And the lower laser level is now separated from the source level. And the gap of energy is so chosen, that is, we would choose the medium with such energy level configuration that the lower energy level is separated from the source level by enough gap in energy, so that if you plug in these values in the Boltzmann distribution, you will see that the thermal population to begin with in the lower energy level is almost zero. It is practically empty. Therefore, you see, if you transfer only one atom now to the upper laser level, of course, higher pump level, it is only one atom. This is zero. There is no atom. So you have created population inversion. Earlier, to create this condition, you have to transfer a lot of atoms from the ground to this level, expending huge amount of energy. And now you have achieved this just by transferring one atom. The great advantage. And not only that, this atom, when it comes down, emitting, of course, the photon, this atom then immediately comes down, relaxes back to the source level, and therefore it is once again available for continuation the process of lasing. And thus you see such a four-level energy based laser is conducive for maintaining population inversion in a continuous manner to yield CW lasing. Now, the question that we need to ask here, can we increase the power of such a CW laser indefinitely? Or what would be the challenges that we'll have to overcome if we have to continuously increase the output power of such a CW? This, of course, is based on a four-level energy scheme. To understand this, let us go a bit deeper into this energy level scheme. You see, for extraction of an photon from this system, whose energy is E2 minus E1, the photon that will be emitted from this transition will have an energy which will be E2 minus E1, right? To extract a photon of this much energy, you will have to expand an energy which is E3, because for creation of this population inversion, you have to, or to take this atom from here to here, you have to spend E3 amount of. Now, this energy which you have already spent, E2 minus E1, that is from the energy that you have spent, which is E3, the energy that you have extracted from this energy is photon, which is E2 minus E1. That means this much energy stays back into the system. So what happens to this energy? This energy would eventually realize the heat. That means it would increase the temperature of the medium. So what happens if the temperature increases? If the temperature increases, then this level starts getting heated, because thermal population will now begin to appear in this level because we are increasing the temperature. So you please take a look on Boltzmann distribution, thermal distribution of population that we have studied in quite detail, you will see that if you increase the temperature, this level now starts getting populated. So if you increase the intensity of pumping in order to increase the output power of the laser, that means you are trying to increase the population inversion. Then another effect that is simultaneously taking place is increasing the temperature, which tends to reduce the population. So in one way, you're trying to increase the population inversion by increasing the intensity of pumping. At the same time, this is also tending to reduce the population inversion. Therefore, as you see, until and unless you have extracted this heat, remove the heat from the system, you cannot increase the output power of the laser. So in order to increase the output power, you have to increase the intensity of pumping, and at the same time, you will have to also remove the dissipated heat to keep the temperature at ambient condition if you have to increase the output power. Now, there is of course a limit up to which you can extract the heat from the system. And thus, you cannot increase the output power of the laser indefinitely, of course, up to your point. So then, what will be the remedy if you have to still increase the output power of the laser? Well, the remedy would be to operate the laser in pulsed mode. See, to appreciate this point, and how by pulsing the laser you can increase the output power of the laser, I will just take an example. Suppose we have a CW laser which is giving 1 watt output power. So this is our power and this is time. So the laser is producing continuous power, that is 1 watt in time. Now we want to increase the output power. No, just a moment. Yeah, we want to increase the output. If you try to increase the output power by increasing the pump power, then of course there may be slight increase in. Eventually, there will be more dissipation of energy, which will heat up the medium, and the power will tend to reduce. To appreciate this point, let us assume that this laser operates at 10% electro-optic efficiency or 10% operating efficiency. That means we are actually we are pumping it at a power with 10 watt. That 10% efficiency, we are producing 1 watt as the optical output. So now 10 watt means in every second we are putting 10 joule of energy into the medium, and we are getting 1 watt as the output, 1 joule as the output in every 1 second. So suppose this is my 1 second. So in 1 second, we have dissipated 10 joule of in 1 second. And in 1 second, we have got 1 joule output. This is output. Now I want to increase this output power by increasing the pump. If we make the pump power high, suppose we are pumping 11. So true, the power may increase slightly in the beginning, but then because we are putting in more energy, there will be more dissipation of heat. And unless we have extracted that, removed that extra heat that has been, energy that has been dissipated as heat, the power. So the best solution to achieve higher power without, of course, increasing the power of removing of heat would be to pulse the laser. You see, you do one thing. Instead of pumping the 10 joule of energy in 1 second, you pump 10 joule of energy in half second, half of the time. You pump this 10 joule of energy in half second. That means your power, you are now pumping. So here actually the pumping power, average pumping power has been 20 watt because you have dumped 10 joule of energy in half second to 20 watt. So the laser now would also produce over that half second, it will produce a power which power would be correspondingly higher. This is the laser output. Now you, for the next half second, you don't put any energy. So the temperature that has increased will allow it to thermalize so that it comes to ambient condition at this point. So once again, you dump your next part. So once the ambient condition has returned, you dump your second pulse for the next half second. This is your second pulse, pump pulse. And once again, then the lasing would occur for this half second. And then for next half second, you again, there is no energy that is being pumped. So once again, you allow this half second for the condition to return into the ambient situation, where you once again pump the next part. This way, you see, you will be able to generate pulses. However, although the average power will still remain same as 1 watt, if you take the average, but the peak power of these pulses can rise much beyond 1 watt. Because in some of the application, probably 1 watt will not suffice. You may need a power which is more than 1 watt. So this way you can generate, pulse the laser, and you can continue to increase the output power without taking any further precautionary measure like removal of heat and water. So I would end here today. In the next class, we will see how the pump energy depends, the peak power of the pulse depends on the pump.